I'm recording. Let's see. I want to go through the calendar, and then I want to show you how to get to the recordings for this week. So this was last week. This was our lost week. I recorded videos for that part. The recordings are, hour and 20 is what we have per class. So that's 2 hours and 40 minutes. My total comes to 2 hours and 43 minutes. So I really was able to keep it to our legal time, not our legal time, because sometimes you guys stick around a little while longer. But because remember the first video, there's a 37-minute chunk missing. I'll show you that in a minute. We're right here right now on 3.1. We're fully on schedule. We'll get into 3.2 today and finish up. Then next week, we'll review, on Monday, we'll do 3.4. On Wednesday, we'll review, and you'll have until Friday. Very much the same pattern as test 1. This is week 8. We'll cover week 8, and then we have spring break after that. The middle week of March, like it starts Sunday, March 14th, is where spring break starts. So we still have 3 more weeks of class before we break again. Okay, let me wander with you over to, nope, that's not what I want to do. Let's see. I'm going to have to start this process. Okay. Let me take you to, I got a few texts or emails saying that you didn't know where the recordings were. So go back to Blackboard Collaborate Ultra, this hamburger menu up here, click on it, and then it opens up to this. Hit the recordings, and then you got to go way down here where it starts college algebra, because I recorded it at the course room. So it shows up a little different. This is Monday, February 15th. I come back in at 37 minutes. So watch the first 3 minutes. That was actual recording. And then I went on a rolling blackout. So I come back in at the 37-minute mark. So this looks like it's over an hour. It's not. It's like 25 minutes. This one is 33 minutes. This one is 14. And then I'm showing you one problem on my math lab. That's Monday. And then Wednesday was 34-minute, a 22-minute, and a 28-minute. Those sections there, as I had to do them in pieces because of the rolling blackout-ness. I think that's it there. That's where you go to right up here with the hamburger menu and go back to sessions, and then we're back where we were. So let me take us back here. I'm going to stop that and go back to my dot cam. Okay, let's get going. Questions before we get started? Anybody, anything? A couple of my links were bad on 2.5. 2.5 didn't transfer from Word into Google Slides. So Chloe wrote me. I tried a couple different ways. I know I emailed you photographs of them. And then I woke up the next morning and said, duh, PDFs. So I turned it into a PDF, and it's back at the slide as a PDF. Almost, 3/4 of you have hundreds on that section, so you're way beyond that. The next 2 sections are easier and quicker. They're not necessarily fewer problems, but they go quicker. So I'm excited about you getting through with that. 2.5 we'll make 2.5. Having done 2.5, we'll make 3.1 today easier, and I'm excited about that too. Okay, let's get going. In this worksheet, we're going to be looking more particularly at parabolas. We're going to study them a little bit more, not in gross detail, just a little bit more. Okay, so let's go through and find these aspects of this parabola. First off, I'm going to see it's an x squared, so I know it's a parabola, and I'm just going to draw myself a little picture there. That tells me it's a parabola. This is a normal parabola. There's nothing weird about this one. And as we go through, you'll see what makes them a little unusual. But just having the x squared piece there tells me that's a parabola. I know that normally it would sit here at 0, 0, but we've got a transformation on it. The vertex is always going to be the opposite of what you see between the x and the exponent, the opposite of what sits here on the function of x itself. So the opposite of a -6 is a +6, and then the same as what sits back at the back. So 6, 7 is the new vertex of this parabola that normally sits right there at 0, 0 and has arms going up like that. This one will be at 6, 7. We'll draw it in a minute. I'm going to put off drawing it until a second later because of something they do to you in my math lab that I want you to be aware of. Axis of symmetry will be a vertical line through the parabola that will go through the vertex. And it will always be an x equals line because that's what vertical lines are. They're all x equals. And it'll always be x equals the x number, x equals 6. We'll look at that in just a second. But you've got an x right there that tells you you're going to have an x equals. Let's look at the y-intercept. The y-intercept is where does our parabola cross the y-axis. So that's always going to start with a 0 on the x. So we're just going to plug in a 0 on the x. Go up here and plug in a 0. So 0 minus 6, that's negative 6. Negative 6 squared is 36. And then 36 plus 7 is 43. So the y-intercept, if you're thinking of it as a point, a full point is 0, 43. I think almost all of your problems just ask you for the number itself. So 43 is the y-intercept. Now we don't have a 43 on here. I'll show you what that looks like. In fact, now is a good time. Where I want to draw these graphs is as soon as we finish the y-intercept. So let's see. Our vertex is at 6, 7. Go out 6 and up 7. There's where our vertex starts. That's not where a vertex starts. That's where a vertex is. And then I know it just looks like a normal parabola. There's nothing fancy here. So it's going to be looking like that. Okay, now, what I discovered is some of your parabola problems are matching, in which case this is not going to be a problem at all. But some of them require you to plot another point. And if they require you to plot another point, I know that over 1, up 1, or over 1, up 1 are perfectly good points, but not to my math lab. My math lab wants an x-intercept, which we're never going to have. It's going to go up here. It's never going to come down here and cross the x-axis. Or it wants a y-intercept. So it does not want you to move over 1 and up 1 and plot a point, and then my math lab goes, okay, cool, we can draw it there. They'll do it, but they don't want that. They won't accept it. They'll give you a block saying, okay, cool, you've drawn a parabola, but we want you to use the vertex and y-intercept or x-intercepts. So instead of using these, go use the vertex point and then grab the y-intercept, which is way up here at 0.43, impractical for us in this problem. But I will discuss that with you as we move through the rest of these problems. I'll remind you of that. I did a really crappy job of drawing that one. Okay, so drawn up there, and you will never have to be super detailed on these. The test will be matching. Yeah, Diana?
Could you explain once more how you got the y-intercept, please?
Yes, yes. The y-intercept, anytime you see that word intercept, you're always going to zero out the other variable. So because this says y-intercept, I'm going to put a 0 in for the x, always. All the way down here, I'm going to put a 0 in for the x. I'm going to put a 0 in for the x, etc. Then what I'm going to do with that 0 that's put in for the x is I'm going to put a 0 in right there in the equation. So 0 goes right there. 0 minus 6 gives you negative 6. Negative 6 times negative 6 gives you 36. And then 36 plus 7 gives you 43. So it's just a plug in on the x, plug a 0 in for the x. Anytime you see that word intercept, and we're going to see y-intercept all the way down, anytime you see that word intercept, you're putting a 0 in for the other variable, not the y, but for the x. Is that cool?
Yes, I got it. Thank you.
You're welcome. Okay, let's look at domain range and then minimum maximum.
Can you re-go over how you got the vertex?
Yes, and we're going to do this over and over and over. The vertex is the opposite of what sits between the x and the squared. It's always going to be a liar on the x, always, just like we talked about in 2.5. Always going to be a liar there. So the opposite of a -6 is a +6. And then the number at the back is going to be the same. So the X number will be a liar. The other number will be the same. That's supposed to say same there. Is that good, Kaylina?
Yes.
Okay. All right, let's look at domain. Domain on parabolas is always -infinity to +infinity. This will reach out going all the way on the X. This arm will reach out going all the way on the positive end of the X. Range is trickier. Range is the Y-axis. Not sure why it's trickier, but to our brains it is trickier. I don't have any orange down here, so I'm not using up the thermometer at all. I'm looking, starting down here. Nope, nope, nope. There's no orange. There's no orange. There's no orange on this. Scoot this guy over to the Y-axis to be able to see what you're using up. Scooting him over, I see I start at 7. 7 is the Y number being used here. That's not a coincidence. And we're going to go over this many times. So the range, what we're using up on the Y-axis, what we're using up on the thermometer, when you scoot this figure over, you start using the Y-axis at 7, and it goes up from there. So 7 with a bracket on to infinity. And now this point, the vertex point, is that a minimum or a maximum for the graph? That's the lowest this gets. It's a minimum. So we know we've got a minimum. And it says at X equals, so let's go down here to figure out what the X is. It's a 6. And the minimum itself will always be the Y. The lowest we get on the Y scale is a 7. So it's always, we're going to be putting the X in there for X equals. We're going to be putting the 7 in here. Always we're going to put the X coordinate of the vertex there, the Y coordinate here. The minimum is at 7. That's the minimum this roller coaster goes. The lowest this roller coaster goes is down to 7. And that happens where X equals 6. It's not low at X equals 6. It's low on the Y-axis. So this will always be the Y-axis coordinate. This will always be the X-axis coordinate of the vertex. Okay, let's do that again. This said f of x. That's the same thing as y equals. So this is a y equals. Let's see, it's a parabola also, x squared. I see that's a parabola. But I need y equals. So let's move this guy over across the y-axis. He'll turn into a +7. I said across the y-axis. How about across the equal sign? So that -7 will add 7 there and add 7 there. So we end up with y equals negative parenthesis x minus 1 squared plus 7. Okay, this is going to be a parabola. It's got an x squared, so we know it's a parabola, but it's got a minus sign in front of it. And from section 2.5, and those of you who haven't looked at 2.5, this will be much, much clearer, because that's all we did in 2.5 was talk about the minus signs kind of things. But that means it's going to turn this upside down. So instead of being a parabola that turns up, our parabola is going to go down. So this is an upside down parabola. And the only reason why it's upside down is because that negative sign right front there in front of the x squared piece. So when you've got a negative in front of the x function, you know that your figure is going to go down. It's going to flip across the x-axis. So we know that's going to be the shape. Let's look at the vertex. Same game. Whatever's inside here, that's a liar. So it says -1. I'm going to put a +1. Then the back end, the +7, that's not a liar. That'll be the same. So we're always going to do liar here on the x-axis, on the x function, and then same back here. So in the vertex will, instead of being a -1, will be a +1. This back end piece will be a 7. You ignore that negative. That negative gives you information. The information it gives you is that the thing will flip upside down. Oh, back here on axis of symmetry. X equals 6 is our axis of symmetry. That line, that axis of symmetry is right there. That's the line x equals 6. x equals 6 goes up and down through the point where x is 6. It's parallel to the other axis. So that's an x equals 6 line. That's the axis of symmetry. Okay, so back over here, the axis of symmetry here, it's got an x, so it's always going to be x equals, and just see what x equals. X equals a 1, and maybe I'll remember to put it over here when we do it. The y-intercept. Anytime you see that word intercept, you know you're going to zero out the other variable. So zero out, instead of the y, zero out the x. So I'm going to go up here with my 0 and plug it in. 0 minus 1 is a -1. -1 squared is 1, but it's got a negative in front of it. So it's -1 plus 7, and that gives us a 6. So the y-intercept, where this is going to cross the y-axis, is up here at 0, 6. Let's first, now that we're done with y-intercept, I'm ready to graph this. The vertex is at 1, 7, so go over 1 and up 7. There's the vertex point. And this is what I was telling you, where my math lab does not care that you just draw in like you know, okay, let me start over. There's the vertex point. I know this is going to go down. I know this is ponytails here instead of a bucket. So that negative sign there tells me that. So on my math lab, if you're matching, you're good. But if you're having to draw it yourself, click on the graph. It will upload it'll create a palette. Click on the parabola, put the vertex point in there, and then you've got to put another point. If you were to put that point, it will draw it in there for you. It'll say, okay, we know what you want, and it'll draw it in, and then you check it, and it'll say, you know what? No, that's not good enough. We need a y-intercept or an x-intercept point. So they want the y-intercept, 0, 6. They want that. Then you hit submit. So we've got this parabola doing this kind of thing right here. The domain for all parabolas is -infinity to +infinity. You can go down right now and draw in the domain, right in the domain for every one of them, because this line, this part of the domain, this part of the parabola will extend to -2. It'll go out to -3, -4. It'll continue and use up all the negative. This will do the same thing on the other side. So domain is -infinity to +infinity. Range starts at the bottom. Oh yeah, these ponytails go all the way down to the bottom. So we start at -infinity on the y-axis. You're asked, what are you using up on the thermometer? So yeah, these go all the way down to the bottom. Now let's see how far up we go. We're still using the y-axis. Still, these are covering the y-axis. Squish this into the y-axis. Think of it that way. Still using it, oh, right there is the topmost place we use it. We don't go up here. The topmost place for this parabola is at 7. So it stops at 7. It uses up 7. That's the y-coordinate there. The y-coordinate will always be involved in the range, either as the lowest point or as the highest point in this case. Let me put in the axis of symmetry. X equals 1. Left-hand side is the same as what's happened on the right-hand side of this parabola. Okay, is the vertex point a minimum or a maximum? Let's see, that's the highest our roller coaster gets, so it's a maximum. And where does it hit on the thermometer? It hits at 7. So 7 is the maximum point. That happens where x equals 1. Remember, I told you, use the vertex point for this. Where it happens is at 1, but the actual highest point it reaches, height is on the y-axis. So the highest point it reaches is 7, and that happens where x equals 1. So this will always be the y-axis coordinate of the vertex. This will always be the x-axis coordinate of the vertex. What it is, how high it gets, that's on the y-axis. That measures height. Where it happens will be on the x-axis. Okay, let's keep moving. There's an x squared. That's going to be a parabola. There's no negative sign in front, so I know that this is going to look like that. It's going to be like a bucket. But it's got a number in front. And just like we did in 2.5, when it's got a number in front, that tells you something. That tells you, in this case, that we're going to be stretching these guys. Instead of this relaxed 1 hardness that it's got a 3. So these lines are going to be pulled tighter. This is going to be a skinnier parabola. Now, in 2.5, we had to build a table and figure out exactly where it was. That's not going to happen this time. We don't want as much detail in this one. And I'll show you what I'm talking about as we go through these pieces. So the first thing we want is the vertex. This piece is a liar, and there's no distribution going on. This is not difficult. This is just pull off the information from here off of that. So this is a liar, so the x-coordinate is a -2. This will be the same, so we've got a 5. I'm going to wait to graph that because I want to know another detail here. So liar, same, so -2, +5 will be the vertex point of this parabola. The axis of symmetry, that x right there tells you this axis of symmetry will be an x equals, and look and see what the x is. The x does equal. It equals -2. The y-intercept, let me graph this over here just a little bit for you to see it. -2, +5, 1, 2, 3, 4, 5, right there. I know it's going up because there's a positive in front. That's not a negative. Remember, this one had a negative, and so it faced down. It was ponytails. But this is a positive, so it's going to be a bucket. So it's going to do this kind of thing, but I need to know where I need another point. Some of your graphs that you'll have at my Match Lab, you'll be matching, and then it'll be simple. You'll just match it to that. You know, draw in a bucket or look for the bucket. You don't even have to draw it in. Just look for it if you're matching. But on the ones where they want you to do the actual construction of the graph, you're going to need more than just, you know, like, where do I put this other point? You're going to need a y-intercept or an x-intercept. But this guy is never going to cross the x-axis. He's never coming down here. He's just hanging out up here. So we're going to have to find the y-intercept. Let's do that. Plug in a 0 right there, and then just go through parentheses. 0 + 2 is 2. Exponents, we're just doing PEMDAS. Exponent squares it. So 2 squared is 4. Multiplication, 3 × 4 is 12. And then addition, 12 + 5 is 17. So the y-intercept is at 0, 17. Now, of course, on this graph, we're not going to do that. But 0, 17 is way up here. So this is going to be a skinny little graph, super skinny graph, like that, because it's 3 times skinnier than a normal graph. The normal one, if this were the vertex point, over 1, up 1, over 1, up 1, it'd be, you know, good and round and fat. This orange one is this one because he's got a 3 in front of him. So it pulls these up at a strength of 3 instead of a relaxed strength of a 1 in front. So it just means it's going to be a skinny graph when it's got a big number here. Now, 0, 17 is where this guy is supposed to go through the y-axis, way up here somewhere. Domain for this, still on the orange, -infinity to +infinity. It's going to be using up the entire x-axis. The range, scoot the orange over to the y-axis, over to the thermometer to figure out the range. You're not using anything down here. You know, we start with -infinity, but this guy's not using any of that up. The first time, scoot him over. The first time he starts using up the y-axis is there at 5, right there. That's the y number that he uses up first. So he starts at 5, and then those arms go way up to infinity. Okay, let's look at this vertex point and decide if it's a minimum or a maximum. It's the lowest point the orange graph gets to, so it's a minimum. And that minimum, how low does it get on the thermometer? It gets to 5, and that happens where x equals a -2. Again, use the vertex points for that place. Always this will be the y value, how high or how low it gets. And then where that happens is on the x-axis, and they tell you x equals. So if you get confused, you've got it told to you there. Okay, let's look at our next one. This guy is not set up similarly. It doesn't have this set of parentheses where we do the liar thing and the same thing. This is the other kind of presentation of a parabola. I see it's a parabola because it says x squared, so I know it's going to be a parabola. And it is positive, so I know it's going to be that shape. I know it's going to open up. It's going to be a bucket. No doubt about that. But I don't know what the vertex point is going to be. That's a bit more complicated with this mess. Let me show you what it's going to be. The x coordinate is going to be negative b over 2a. So, you know, that's an a and a b right there. So let's find the x coordinate of our vertex point. Put a negative there, then a b. Let's see, the b is negative 20. So I've got a double negative there. You know what we're going to do with that? Over 2 times a. 2 times a is a 5. So that's a negative right there. I put the negative right there. Be careful that you include that every stinking time. Then b itself has a negative, so I've got a negative 20. So minus a minus is plus a plus. So I get 20 over 10, and that gives me a 2. That tells me that the x coordinate here is a 2, right there. How do I get the y? I have to plug in the 2 for the x. I'm going to plug in a 2 right there for x squared and right there for x. So the way this looks in math books is get the x and then plug it in. That's what they do. They call this point negative b over 2a to get the x, and then f of negative b over 2a. And that just means plug in the number that you got. Plug it in up here. So we're going to use negative b over 2a to get the x coordinate, and then we're going to just plug it in. Plug in the x right there, plug in the x right there to get the y coordinate. So that'll be 5 times 2 squared minus 20 times 2 plus 5. I'm just plugging in a 2 everywhere I find an x. Do exponents first. So I get 20 minus 40 plus 5. 20 minus 40. Be careful, you don't add these two and then say minus 45. This 5 is a positive 5, not a negative 5. So 20, I mean, if you're comfortable doing this, do it any way you want, but be sure you're getting the right answer. 20 minus 40 is negative 20. Negative 20 plus 5 is negative 15. So we get 2, negative 15 is our vertex. We're going to scale this differently so it'll fit, because you need some practice with different scales. We're going to work, I know you've hit them once or twice, we're going to work on them a little bit more. So axis of symmetry, x equals 2. I did not put in the axis of symmetry here. Let's go back and let me repair that. X equals negative 2 is that line right there. X equals negative 2 is the line of symmetry that runs through the belly button, through the nose of the rat, whatever you want to call it. Okay, Y-intercept. No difference there. If you see the word intercept, that means put in an x, put in a 0 for the other variable. So I'm putting in a 0 not for y, but for x, and then plugging it in. Okay, the difficulty that this was, the pain in the butt that this was, rather than just pulling the numbers off, is made up for here. 0, put it in, gone. 0 there, gone, and you've got a 5 right there. So life is a lot easier when you're finding the y-intercept, when you're plugging in a 0. 5 times 0, 20 times 0, you're just left with the constant back at the back. Okay, let's go graph this. 2, negative 15. Okay, my x scale is okay. I got a 2 on that, but I don't have a negative 15 here. So let's grade this by 2s. This will be a negative 2 on the y-axis, negative 4, negative 6, negative 8, negative 10, negative 12, negative 14. So it's going to be a half a step lower than that, even. Half a step lower than this negative 14. So 2, 1, 2, x-axis will still be doing by ones. It's not real legal when you're proving a point, like if you're writing if you're building a graph for, you know, like a newspaper or something online, or really anything where you're trying to prove a point. It's sort of illegal to have different grades on different axes, especially if they're measuring the same thing. If they're measuring different things, you can do an argument. But that's what we're going to do here. So too bad. 1, 2 takes us out to here, and then negative 15, we've got an altered scale. Negative 14, negative 15 takes us right there. And now this is a really good example of what my math lab wants from you. They do not want you to, after you put the vertex point in there, just to slap something on there. They want either an x-intercept, and we have not found those. Don't worry about those for right now. Or a y-intercept. Well, we have found a y-intercept. So when you tell my math lab what you want, you will just hit 0, 5. That's 2, 4, 6. So 5 is right there in the middle. And that's enough for my math lab because it knows that parabolas are symmetrical. So it knows that when you tell them you want that point, it knows you also are matching it to that point right there. Let me do that with orange. It knows you're doing that point. So here we've got this super skinny parabola because there's a 5 in front. That's even skinnier than our 3 parabola. All right. We'll do another one where we change one of the axes so you can have some little practice with that. Domain, same game. Yes, Diana.
How did you say you know whenever you're supposed to find the vertex, like the equation that you did? Is it because of the 3 in front of the x plus 2 squared?
Okay, you're talking about this one up here. Right?
Yes. Oh no, sorry. So then the one that we were just working with, the one that you
Okay.
did negative b over 2a. You said
Yes.
you had to find the vertex. How would we know when we need to find the vertex? Like when
How
we
will you know
equation.
when you need to use this method versus this method?
Yes, ma'am.
Okay, that's really easy. If it's got a set of parentheses for you, you do it the easy way. Opposite of that, same as that, negative 2, 5. This previous one, opposite of that number, same as that number. It's really easy when they've got the set of parentheses set up for you. The other way is there is no set of parentheses. They've got an x squared, an x, and a number. That's when you got to go through the negative b over 2a. And we'll do it again in the next page. You okay with that?
Yeah, I got it. I totally missed the parentheses. Thank you.
You're welcome. This is new. You know, I get that. That's what learning's about. So keep asking. I appreciate it. Okay, the domain here on all parabolas, negative infinity to positive infinity, we're good. Range, that's a different thing. Range is asking you to squish it in to the y-axis and see what got used up. Nothing gets used up down here at the bottom of your page. Nothing. This graph doesn't start using up the y-axis until negative 15, which we didn't quite get to, but it felt like it. So negative 15 on up is our range. Negative 15 on up to infinity. Notice that the range number will always be involved one way or the other, either as the start or as the finish of our range number. Okay, this is the lowest point this gets, so it's a minimum. That minimum, the coldest it got was negative 15, and that happened where x equals 2. Put the numbers in place. Okay, I think we are good. Yeah, ready to go to the next page. Okay, we've got another problem similar. No sets of parentheses on this one, so we're going to do a negative b over 2a, and you can see the same thing's going to happen here. So we'll get a little bit of practice at that. So let's first look and see what we've got. I've got an x squared, so I know it's a parabola. It doesn't have a negative on it, so I know it is that away. It's a normal parabola. Now I need to find the vertex point of it. It does not have a set of parentheses, so I'm going to use negative b over 2a to find the x coordinate. So negative, put that first, then b is a 4, over 2 times a is a 2. So negative 4 over 4 is a negative 1. So the x coordinate of the vertex point is a negative 1. Now I'm going to have to plug that in up here. That's the thing. So it's negative b over 2a and then f of negative b over 2a, which just means plug it in. Plug in what you got. So let's take this negative 1 and plug it in right there. That'll be 2 times negative 1 squared plus 4 times negative 1 minus 9. That's the math we're going to do. Negative 1 squared is a 1. 2 times 1 is a 2. 4 times negative 1 is negative 4. So I'm getting negative 11 out of that. So negative 1, negative 11 is the vertex point. Let's go over here and plot that. We're going to keep the x-axis just 1 unit equals 1 because we've got room to find a negative 1. That's easy enough. But let's change the y-axis so that we have got room to fit in 11. So I'm going to do negative 2 on this one, negative 4, negative 6, negative 8, negative 10, and negative 12. And then, of course, negative 14. Okay, I'll worry about that in a second. Axis of symmetry, x equals negative 1. That's where the line down the middle of the vertex point will go. Y-intercept, stick in a 0 for the x's. That'll zero that piece out, that'll zero that term out, and we'll have a negative 9 to be our y-intercept. Okay, let's go graph this. Start with the coordinates, negative 1, negative 11. Now there's negative 10 right on that target, but you're going to have to go down halfway into that space to get to negative 11. And then my math lab will want another point. Use the y-intercept. 0, negative 9 is right there. It will know that there is this axis of symmetry happening here. It will understand that if you have drawn in x equals negative 1, if you have drawn that in, that means this, well, you wouldn't have drawn this in. I don't think yours ever require the axis to be drawn in. It may, but you know, whatever, you figure it out. But it understands that parabolas are symmetrical about that x line. So it knows that if it has put 1 over there, it's also going to put the other part over there, and it knows how to draw that in then. So you'll have to do very little. The trickiest part, I think, in my math lab is getting, after you get the vertex point, getting another point drawn in, and that'll just be the y-intercept. Okay, domain, negative infinity to positive infinity. Range, where do we pick up the y-axis? Right there at negative 11 and go on up. So negative 11 on up to infinity. This is a minimum. That's as low as our little guy gets. Where is that minimum? How low does he get? He gets as low as negative 11, and that happens where x equals negative 1. Okay, let's do this one more time, and then we're going to play around with some of them. It asks you to do this without graphing, so we're not going to get as involved in this one. Let's look at it, though, and think about it. It's x squared, so think about what it's going to look like. That's going to look like a parabola. It's got a negative in front of it. So it's going to be going down like that. It's ponytails. So if that's what it's going to look like, does it have a minimum or a maximum? Well, it's going to go up here, and it's going to stop, and it's going to come back down. So it's got a maximum. It's going to get as high, that's as high as it's going to get, that vertex point right there. It doesn't have a minimum. These two ponytails go all the way down to negative infinity. So it will not have a minimum. Now we're going to need to know the vertex point to put the x-coordinate there and the y-coordinate there. So let's do that. Because this does not have parentheses, you're going to have to do that negative b over 2a thing. So let's see, we'll have a negative and then a 12 over 2 times a, and a is a negative 3. So we're getting negative 12 over negative 6, which is a 2. So I know that the vertex point, which they didn't ask me for the vertex point, but I know that the vertex is going to be 2, so the x will be a 2. Now I have to plug that 2 in. So it's negative 3 times 2 squared plus 12 times 2 minus 5. 2 squared is 4. Negative 3 times 4 is negative 12. We get a positive 12 minus 5. That gives us a 7. So the maximum, the highest this is going to get is 7, and that's going to happen at x equals 2. The domain is negative infinity to positive infinity, always, always, always. And then the range, it starts down here at negative infinity, and then it's going to go all the way up to the y-coordinate, to the 7. Now, you may not be able to really get a feel for that without graphing, and I completely understand that. I need a picture when I do these. So I left you with a picture here. Let's look at that. We figured with negative b over 2a, we got the 2, 7 business going. So over 2, up 7. And then we don't have a y-intercept, but we could put in a 0 and get a 0, negative 5. So this is going to be down here at 1, 2, 3, 4, 5. And even if you don't get that picky, even if you're not exactly sure there and you're just sketching something in, that's fine. That will guide you to saying that, okay, we've got a maximum, and then how high does it get? It gets up to 7. That happens at 2. The domain is always negative infinity to positive infinity, and the range will start at negative infinity and go up to the 7. So even though they say without graphing, don't feel like you're cheating if you don't scribble something down that makes it look about right to you. Feel free to do that. I mean, you know, I'm not going to tie your hands behind your back and make you guess with your eyes shut. That's silliness. Do the best you can, and you don't have to be able to do these without drawing them. If you cannot visualize them, I completely understand that. Sketch it. Okay, next one. The vertex point is negative 5, negative 4, and the parabola opens up. So I know we're looking like that. Minimum or maximum? Okay, well, the x equals negative 5, and the y-coordinate is a negative 4. So I know that, let's see, this is the vertex point right there. That's a minimum. That's the lowest it gets. Okay. The domain is negative infinity to positive infinity. And the range, I'm not going down here. I don't start going up until I hit the y-coordinate, which is negative 4, and it goes on up to infinity. If that's just not what you're capable of, no problem. Draw it. Negative 5, negative 4, 1, 2, 3, 4, yeah. And then it opens up, so it's doing something like that. And then now maybe you can say, okay, that's a minimum. It happens at negative 4, and x is negative 5. The domain is always going to be negative infinity to positive infinity. And the range, I'm not using anything up down here. Nope, nope, nope. Scoot it over to the y-axis. I don't start using it up till negative 4, and I go up to infinity. So use the little graph if you need to, if you want to, if it just makes life a little bit simpler for you. Okay, let's draw this. Let's see what we can do about drawing this. Or if you don't want to, just they're asking you for the domain and the range here. Domain, guarantee, negative infinity to positive infinity, promise. The range, maybe you need a little bit more help. I certainly need a little more help. I need a little bit of a picture here. So they're telling us the maximum is 3 at x equals negative 2. that tells me that the vertex was -2, +3. So let me go find that. -2, +3 is right there. And it says this is a maximum. So that's my roller coaster coming up. That's its height, and then it goes back down. So the range now I can see starts down here at -infinity and goes up to the y-axis. Shove this over to the y when you're working on the range. Goes as high as 3. And it uses 3. And it's going to use that range number from the vertex point. So feel free to draw if that's going to make life a little easier for you. Okie doke. Let's see what we got next. Last page of 3.1, and this is all of 3.1 is on worksheets. Let's see. Write an equation in standard form of the parabola. Okay, Diana asked that question about this is standard form when it's f of x equals, like x minus 3 squared plus 5. That's called standard form when it's got the parentheses. So we're definitely going to be using the parentheses, the easier setup where this is a liar and that tells the truth. Write an equation in standard form of the parabola that has the same shape as the graph of that. Well, let's see what this has. All this says is that we've got a parabola. He's going to open up because there's not a negative in front, and he's got a 10 on him. That means these are really going to be skinny. I mean, it's going to be really a narrow parabola, goofy looking parabola. Big deal, you don't care. F of x equals, put the 10 out there, set this up. Now, we know that it needs to go through 411. The vertex point right there wants to be 411. So in here, you want the x coordinate to be a liar. So instead of a +4, you want to put a -4. That will yield a x coordinate of +4. Then the 11 goes back out here. And that is it. That's all you have to do. It's so much easier than lines. So we take the basic format, 10 times a parabola. There's 10 times a parabola. Our parabola will now have a vertex point of +4, +11, which is what they wanted. Okay, write an equation of the parabola that has the same shape as the graph of this one, 4 times a parabola, or -4 times a parabola. So this one will open that way, this one will open that way. We don't know which way they want yet. It says with the given minimum. Okay, if we're looking at a minimum, that one has a minimum. That's the lowest that vertex point gets. This one, though, has a maximum. So this is not our answer. That's not what we're going after. So what we want to do in this one is we want to use this guy, 4 times the parabola. So let's do the same thing we were doing up here. F of x equals 4 times the parabola. And now let's use this information. The minimum is at 0. The x is at 18. So the vertex was 18, 0. That's the vertex point. If you want to think about it on a graph, it's way out there. Go out 18, don't go up or down. That's the vertex point. So there's our graph sitting way out there. Now we need to fill this in. So what we've got here is an x that says positive. You want to make this a liar, so -18. And then the y change is a +0, but nobody says that. So we end up with f of x equals 4 times the parabola, x minus 18 squared, because we were given this piece of information. Okay, this last one here is just kind of a little bit of fun. Let's see, I wanted to be done with this at 9, good, and moving on to the other one. So we got 10 minutes to do this one stinky little problem. A ball is thrown upward and outward from a height of 9 feet. So let's say there's a, well, let's keep reading. The height of the ball, f of x, in feet, can be modeled by there's our equation. That's going to matter. There's our equation. Where x is the ball's horizontal distance, so this will be horizontal distance out here. How far the ball travels horizontally in feet from where it was thrown. Okay, they told us that y, remember that's the same thing as y, is the height of the ball. So the height of the ball is on the y-axis, and that's in feet also. Okay, let's see. The ball is thrown upward and outward from a height of 9 feet. I know the last thing they do to tell you is to graph, but I think it's much easier to visualize if we look at the graph as we go. So I'm going to do that. Okay, nobody is 9 feet tall. So let's say that here at 0 feet, where the ground is, we're going to build you a box, and then you get to stand on this box. There's you, and you're throwing this ball. So it was thrown from a height of 9 feet. So when you throw this ball, you know what this ball is going to do. It's going to do that. Let me extend this out here. It's going to land on the ground out here somewhere. That's what's going to happen. Oh, that's very pretty looking, except for you. You look a little funny there. Okay, let's see what we've got here. What is the maximum height of the ball? So they're asking you for the point that is right, let's say, I'm looking at the maximum height, say right there, somewhere in there. We're looking for that piece. And how far from where it was thrown does this occur? So they're asking you for that information. How high did it get up? And how far out, how far from where it was thrown does this occur? They're asking you for the x and the y of that coordinate. So that's just the vertex point. That's what we're looking for here. We are looking for the vertex point of that equation. This is not nice and neat in little parentheses. It's not in standard form. So let's use our little negative b over 2a to solve this. So put a negative there, and then grab the b number, 1.4, over 2 times, and the a number is a negative 0.2. Okay, so I got a negative 1.4 times negative 0.4. Put that in your calculator, negative 1.4 divided by negative 0.4, and you get 3.5. That's the x coordinate of this guy, of our vertex point, of our maximum here. So that's the x point right here is 3.5 feet. So that ball goes out 3.5 feet. Let's figure out how high it was. This is 9 feet. You standing on this box and throwing the ball from 9 feet. That's where it left your hand. Let's see how high you threw it up. That's the y coordinate of this point. So far we know this point is 3.5. We don't know the y coordinate. Always take the 3.5 and plug him into the equation. I know it's messier this time. We're not going to be able to do it super easily, but you've got a calculator. So let's see what we're going to do here. I'm going to do it up here. So we've got negative 0.2 times 3.5 squared plus 1.4 times 3.5 plus 9. Okay. 3.5 squared, 3.5 times 3.5, I get 12.25. Now I'm going to multiply it times negative 0.2 times negative 0.2, and we get a negative 2.45 there. Then I got 1.4 times 3.5, and I get plus 4.9 plus 9. Okay, negative 2.45 plus 4.9 plus 9 gives me 11.45. 11.45. That tells me that this height right there, the height that the ball got, was 11.45 feet, 12 feet, well, 11.5 feet, 11.5 feet. So the vertex point here is 3.5, 11.45. That's just a plug-in. Okay, B says, how far does the ball travel horizontally before hitting the ground? How far out here? What's that point? That's what they're asking us. Where is that? Well, it'll be an X point. It'll go out to the X, and then the Y is a 0 because it doesn't go up or down. We want to know what is the X coordinate where Y is 0. That's when it hits the ground. When the Y axis, how tall it is 0. So unfortunately, well, whatever. It's a pain in the butt to do that. What we're saying here is make the Y be a 0. There's the Y. We're going to take out the f of x and put a 0. So we've got, I'm going to put it over here because I don't have quite, I got room here. I'm good. So we've got 0 equals negative 0.2x squared plus 1.4x plus 9. This is a quadratic equation, x squared x. We've got a 0 there. We're not going to factor this into two sets of parentheses. Let's use quadratic formula. So x equals negative, b is a 1.4, plus or minus b squared minus 4 times a is a negative 0.2 times c is a 9. And remember, I've been telling you, take a second before you go down to 2a and look at these. That's a negative times a positive. So this is going to end up being a plus right there. We're going to end up 1.4 squared plus whatever we get for this back here. And all of that over 2 times a, which is negative 0.2. Okay, let's clean this up. X equals negative 1.4 plus or minus 1.4 squared. Let's see if we can't just walk all the way across the calculator, all the way across the radical doing this problem. 1.4 squared, that's going to be humpy 2. And you can hit equal if you want to. So we got 1.96 plus, and then I'm going to do parenthesis, 4 times 0.2 times 9, close the parenthesis, equals. So that business, is just the radical is 9.16 all over, that's negative 0.4. And looky here, just in case you didn't notice it, negative b over 2a, there's negative b, there's 2a. So negative b over 2a, how you get the x coordinate is this front part of the quadratic formula. It's magic. I don't understand how it works, but that's because I haven't explored it a whole lot. I'm not super duper math nerd, just mildly a math nerd. Okay. We want to know where it hits the ground. How far, this is 3.5 feet. How far out does this go? So I don't care that this is exact. The square root of 9 is a 3. I'm going to be good for that. So my problem is negative 1.4 plus or minus 3 over negative 0.4. That's what I'm going to work on. I rounded this, and if you put it in your calculator, you get 3.02, I think. That's close enough. Let's just call it 3. We're going to be good enough there. So we've got 2 places that this is supposed to land on the ground. We've got a negative 1.4 plus 3 over negative 0.4, and we've got a negative 1.4 minus 3 over negative 0.4. Let's work on both of those. Negative 1.4 plus 3 equals, divided by negative 0.4 gives me negative 4. X equals negative 4. That's telling me that the ball lands back here. Oh, looky there. That's what the parabola would do if we allowed it to go back here. That's a fuller parabola, negative 4. But that's not where the ball lands because this doesn't exist in real life back here. So this one is no good. Let's try this one. Negative 1.4 minus 3 equals, and then divided by negative 0.4 gives us 11. Oh, that's a nice number. Way out here, this is at 11. X equals 11 right there. So our ball launches from 9 feet, goes up another couple of feet, goes down to 11 feet out away from us. And then the third thing asked you to graph the path of the ball, and we did that as we were going. Okay, that took me 1 minute longer than I wanted to take on 3.1. That's fine. Let's look at 3.2. 3.2, we're going to get some ways into this. We're not going to do the nitty-gritty. So when you go to keep up with homework, stop when it gets nasty, and it will get nasty on 3.2. What we're going to do on Wednesday gets nasty. Let's look at 3.2. This is polynomial functions and their graphs. We will graph on Wednesday. We'll just dive in on Wednesday. Now we got to learn a few things. We're going to look at some polynomial functions, and we're going to come up with their degree and their leading coefficient. Okay, let me give you some examples. Let's say we've got negative 3x to the 5th times x plus 4 times x minus 3. When they are multiplied together, we're going to have to combine them up. We're going to have to multiply them out to come up with the degree. But no worries, we're not going to do all this math. We're just looking at the x. So when we're coming up with the degree of this, it's going to be, there's an x to the 5th, so I got to worry about him. Here's an x to the 1st, and here's another x to the 1st. So if we were to throw this all down, and we're not going to, we're looking at the degree. That'll be a 5 plus 1 plus 1 more. So the degree here is 7. Look at the exponent only. 5, find another x, 1, find another x, 1. 5 plus 1 plus 1 gives us 7. So the degree here of this, it would be an equation like f of x equals. The degree of that polynomial function is a 7. Notice that that is an odd number. They're interested in that, and I'll show you why they're interested in that in a minute. So it is x to the 7th, and that's an odd number. 7 is odd. Next thing we want is the leading coefficient. We'll abbreviate that LC. The leading coefficient means what's the number in front of the x to the 7th? And that's going to be a negative 3. Not real fancy, very simple. Let's do another one. Let's look at f of x equals, let's say 2x squared times x minus 3 squared times x plus 5. Okay, the degree here, we've got an x squared, so we've got a 2 we got to worry about. We've got an x squared. Oh, there's another 2. Be careful. I know there's a 1 there, but it gets squared, so it's a 2. And then we've got a 1 right there. So that was a 2. 2 plus 2 plus 1, 2, 4, 5. So the degree here is 5, and that is an odd number. There are a couple problems where they're interested in that, and you'll see why we care in a little bit. Leading coefficient, super simple, it's a 2. Okay, I've rearranged this a bit, so okay, we're good there. Okay, so next section, is it a polynomial function? Is it a polynomial function? If yes, what is the degree? So we're finding the degree again. You're learning what makes a polynomial function or not, and then we're practicing getting the degree again, because that's really going to matter. Okay, let's look at our first one. We are looking at 1, 2, 3, 4, 5 of them here. 9x squared plus 7x to the 5th. Okay, is this a polynomial function? That means are all of the exponents positive whole numbers? Integers? No, not integers, because integers include the negatives. So we need the natural numbers plus 0. We need whole numbers here. So let's look. We've got a 2 and we got a 5. So is it a polynomial function? Yes. Nothing weird happening there. It's perfectly normal. And if yes, what is the degree? Be careful here. Up here they were multiplied, so you had to throw them all in the hat to get a 7. Here they were multiplied, so you had to throw them all in a hat to get the 5. Here they're added together, so you only look for the big guy. So the biggest exponent I find is a 5. So the degree here is a 5, and of course that's an odd number. So when they're added together, you're not combining. Don't start adding them together. When the terms are added, you're looking at individuals. And in this case, the individual, it has a 5 on him. We're mostly going to work with these that are multiplied together. But when you're doing this, is it a polynomial function? They want the opportunity to give you different ones. Anyway, just roll with it. We'll mostly be doing adding them up. Let's look at a second one. F of x equals 8x to the 8th minus pi, being the coefficient, times x to the 5th plus 1/3 x squared. When you're trying to decide if something is a polynomial function, your only concern is about exponents. 8, that's a natural number, that's a whole number, we're good. 5 is a whole number, that's good. 2 is a whole number, that's good. We don't care that pi has some weirdness to it. We don't care that this is a fraction. We're only looking at exponents and they're all normal. So this is a polynomial function. And then its degree, remember when they're added up separately, you're only looking at the big guy. And be careful because my math lab does this kind of trick to you where they put the big guy at the back. And you go, okay, that's an x squared. Oh, you got to look. So always look around at each exponent. So the degree is an 8, and that is an even number. Let's look at h of x, although it doesn't matter what you call it. 2x to the 5th plus 3x squared plus 7 over x. 7 over x. Okay, is it a polynomial function? There's a 5. There's a 2. Ooh, this guy is in the denominator. Can't have him in the denominator. So if we moved him up, he would end up being a -1 because he's in the wrong place. Negative exponents are not allowed. Now, if you're not real comfortable moving that up, let me move it over here, 7 over x. That's the same thing as 7x to the -1. A guy in the denominator, he has a 1. Move him up, he turns into a negative, and you can't have negatives in polynomial functions. You don't have to get that hairy. You got a 5, you got a 2, and you got something in the denominator, you got a problem. So this is not a polynomial function, and we don't have to worry about the degree. Although I'm hoping that you could determine that if we didn't have this guy here, it would be a 5. Let's look at f of x equals x to the 1/2 minus 9 to the x plus 11. Again, we're looking at the exponents. This has a 1. This, you know, has a 0 if we had to give him one, and that's okay. That's okay. That's not okay. They need to be whole numbers. So this is not a function either. So what do we have? We have in the denominator, we have fractions, and then let's see, our last one is f of x equals x squared over x to the 5th plus 13. Okay, that's another problem because if you were to simplify this, x squared over x to the 5th, all these would be gone. We'd end up with a 1 up there, and we'd end up with 5 minus 2 is 3. And we've got the same problem here that we had here. You can't have the variables in the denominator. So this is not a function. Okay, let's see. Let's look at a vertical line test. Vertical line test for functions. Let me remind you that a function has to pass a vertical line test. So a parabola passes the vertical line test. It is a function. It can't have an inverse. That's 2 points, 2.8, something like that, 2.7 maybe. But that's not what we're concerned about here. We're only concerned about vertical line test. So in a vertical line test situation, we're good. This is a function. We're going to have messier things happening, something like that. That also is a function. It passes the vertical line test. So this is a function. This is a function. Still, we're doing good. What is not a function that we're going to look at sometimes would be something like this. Something like that. Because to be a function, something you didn't know because we didn't have to worry about it, you have to be smooth, you have to be continuous, and you have to rise and fall without boundaries. You will not have to memorize this phrase. It'll be one of the things you have to worry about on a My Math Lab problem. So it has to be smooth. That's smooth. That's continuous. There are no gaps. It has to rise and fall without boundaries. There's no limit. You can get on this roller coaster and keep going. Same thing here. Get on this roller coaster. There's no problem. You get on this roller coaster and there's a problem. You can't ever get to this part of it. So it is smooth, but it is not continuous. This does not ever get you to this piece or to this piece. So this is not a function. We're going to mess with it, but it's not a function. Let me ask you a little bit about that. Okay, here comes the most fun in this section. And I'm serious. We're going to look at what's called end behaviors, and you have to know that before we launch into the last part of 3.2. Falls to the left or right, and then rises to the left or right. We're going to use those phrases here. Let me show you what I mean. Let's see. You know that's a parabola. That's an x squared figure. X to the fourth will have the same end behaviors. They will go up. They'll do some crazy things in there. We don't know what's going to happen in the middle, but x to the fourth will rise to the left and rise to the right. X to the sixth will rise to the left, rise to the right. Notice their degrees are even. X to the eighth, etc. All of those will, they might be a mess. It might look like that, but it'll still, all of these with even degrees will rise to the left and rise to the right. Okay, what happens on a negative x squared? You know that looks like that. It's just an upside down version of that. So that falls to the left and falls to the right. That does. Same thing with negative x to the fourth. It'll fall to the left. I don't know what it'll do in here, but then it'll fall to the right also. Same with negative x to the sixth. It'll fall to the left. It'll do some crazy stuff there, and then it'll fall to the right. Same with negative x to the eighth. It'll fall to the left. It'll fall to the right. Its last thing will be both having ponytails going down because they've got even exponents there, even degrees. Okay, what happens with the thirds? Let's look at what we know with x to the third. You know that that is a snake charmer. Look at what that does. That falls to the left and it rises to the right. That's its end behavior. I know this is almost illegible and maybe is actually illegible. Falls to the left, this left-hand side is falling. It rises to the right-hand side is going up. So same thing with x to the fifth. It's going to fall to the left, something's going to happen in there, and then it's going to rise to the right. It'll get a little bit crazier than a snake. Something will happen, dooey, and then it comes back up rising to the right. Same with x to the 7th. It'll fall to the left, it'll do some crazy stuff, and it'll rise to the right. So all of the odd degree polynomials that we look at will all do the same thing as they leave the picture on the left and as they leave the picture on the right. They will all fall to the left, they will all rise to the right. So all evens will look like parabolas. They'll be uppy-uppies. All negative evens will be downy-downy, just like a parabola. Go back to what you know about a parabola to do all of the evens. They'll all behave the same way. Then the x cubed function falls to the left, rises to the right. So will all of the other odd ones. And then let's look at the negative versions of those. They are going to do the flip of this. They're going to do that, and then do that. They will rise to the left, and they will fall to the right. So we've got a plan for whether it's even or odd, whether it's got a negative in front of it or not. And that's going to drive everything we look at when we get back to this 3.2 on Wednesday. We'll end up with like 7 graphs, and we'll draw them. We'll draw these crazy graphs that are like x to the 8th plus x to the 5th minus x to the 3rd, and we'll figure out what they do with just everything that you already know. You really won't have to learn much of anything new, but you do have to know end behaviors. So we are winding up today. Let me grab our, somebody needs to clean their kitchen counter. That got stuck on the kitchen counter over there. That's disgusting. Let's see, we've done all of 3.1. That was the worksheet. Then we've got 3.2 until you get into the last group of messy graphs. Once you have done a good bit of end behaviors, you're good. And you can pop around and make sure. But I would love for you to get a chance to look at the end behavior part so that you're comfortable with that before Wednesday. Okay, what's going on in your brain? What do we need to worry about? What are you worrying about? Any questions, anything? Good deal, Chloe. Yeah, this is not the toughest stuff we're doing, and we will have a little bit of graphing that is a little shaky for some people because it's got so many steps on 3.2 when we get back on Wednesday. It's not hard, it's just got a lot of steps, and it's like, I want to be done with this problem and move to the next one. And then when we get to 3.3, I'm going to show you how to divide polynomials with synthetic division, and you are going to love me even more than you love me now. It is so fun. It really is fun, and we will use it going forward. So it's a fun skill in 3.3 that you'll use again several times in this class, which is cool. Okay, so I'm going to stop recording.